The night air is thin and glass-like at the summit. You switch off your light and let the darkness settle. The Milky Way rises like a pale river above you, a long, shimmering path of distant suns. Your eyes adjust, slow and careful. Then your guide taps your shoulder and points to a spot just above a jagged ridge, where a faint blur hangs in the sky. It is weaker than most stars. It has no sharp lines. It seems like a flaw in the night itself. That blur is Andromeda. To your unaided sight, it is nothing more than a smudge. Yet it contains more stars than you can count in a lifetime. It is a colossal galaxy that looks smaller than a pinhead because it is millions of light years away. The paradox arrives quietly. The largest structure you can see with the naked eye is also one of the faintest. You live in a universe where size and brightness refuse to line up, where distance tricks your instincts. We are told the universe expands, that distant galaxies move away from us as space stretches. Yet this one, the nearest large galaxy, is not retreating. It is coming closer. Light shows it. Measurements confirm it. This dim blur is falling toward the Milky Way through the dark ocean between galaxies. In a cosmos whose grand rule is separation, these two giants are an exception. They drift inward, pulled by each other's mass. Look again at the blur in your mind. Every photon striking your eye began its journey long before the first human took a step on Earth. It crossed the void with no companion, sliding through silent space. When it left Andromeda, the shape of that galaxy was slightly different. Some of its stars have died since then. Clouds have shifted. New stars have formed. What you see is not Andromeda as it is, but Andromeda as it once was. Time itself stretches inside each faint beam. So the smudge is a messenger. It tells you that Andromeda is a separate realm, not an offshoot of our own. It tells you that the Milky Way is not the whole universe, but one member of a much larger community. It also tells you something harder to accept. These two galaxies are on a slow path toward a future in which their distinct shapes vanish and merge into one. If galaxies were cities, this would be the moment long before sunrise when two skylines, miles apart, begin drifting toward each other without the people below noticing. People did not always know this. For centuries, Andromeda was described as a small cloud. The idea that it might be a separate island of stars was too large to accept. Our own galaxy was assumed to be the entire cosmos. Everything we saw in the sky was believed to belong to our Milky Way. The concept of another galaxy as huge as our own, hanging far beyond its borders, felt unnecessary. Then improved telescopes revealed that the smudge had structure, spiral arms, bright knots, regions that resembled familiar patterns from within our own galaxy. Arguments flared. Was Andromeda a local cloud or a faraway galaxy? Observers gathered evidence, but the photographs remained ambiguous. They showed light, but not distance. The universe was either small or much larger than imagined, and no one could settle the scale. That changed when some of the pulsing stars within the blur were identified as reliable markers of distance. Their rhythmic brightening and dimming acted like cosmic clocks. By comparing their true brightness to their apparent one, astronomers realized the smudge lay far outside the Milky Way. It was not a local haze. It was another galaxy with its own billions of stars. In that moment, the universe expanded in the human mind, and our home shrank from everything to only one among many. In everyday language, we found out that the little blur was too bright to be close and too faint to be small, so it had to be enormous and far away. The night sky became a map with more than one city of stars. The realization came like a quiet shift. The Milky Way gained a neighbor, the smudge gained a name, and humanity gained a larger stage than it knew how to imagine. If this voyage into Andromeda resonates, tap like and subscribe to the Quiet Universe channel. Now return to the contradiction. If the universe expands, why is Andromeda approaching us? The answer lives in the balance between cosmic expansion and local gravity. On very large scales, galaxies drift apart as space grows. But on smaller scales, gravity can overcome that drift. The Milky Way and Andromeda form a pair within a small cluster of galaxies. In such close company, gravity dominates. It is strong enough to pull them toward each other faster than expansion can push them apart. Imagine two enormous ships at sea. The ocean current pulls most ships away from one another, but these two carry such mass that they tug on each other more than the current tugs on them. Their motion is slow but certain. They draw closer over ages. Their lights sparkle in the distance, almost unchanged from night to night, but their paths curve inward. The same is true for galaxies. They move not as solid objects, but as vast swarms of stars, dust, gas, and dark matter. When Andromeda and the Milky Way collide, most stars will pass by without touching. They are too small and too far apart, yet their collective gravity will reshape both galaxies. The spirals will distort. Streams of stars will arc out. Clouds will crash and compress into new bursts of star formation. The night sky from any surviving world will be unrecognizable. This future is billions of years away, but the approach has already begun. When astronomers measure Andromeda's light, they detect a shift that reveals motion toward us. That motion is patient and relentless. A frame taken today will show nearly the same blur as one taken next century. Yet over millions of years, the drift becomes visible when placed on a cosmic clock. Time stretches. Galaxies move. The universe writes its slow stories whether we pay attention or not. A quiet question settles in. What does it mean to exist inside a galaxy that is on a long path toward another? Scale makes the event seem unreal. Human lifetimes are too brief to witness any shift, but your sense of place changes once you understand the arc ahead. The Milky Way is not static. It is a participant in a future transformation. You and everyone you know live in the early chapters of a cosmic merger. Picture again the ridge at night. The person standing there sees a smudge. They do not see two galaxies drifting closer. They do not see the far future where the shapes blend. They do not see the night sky that will shine for the descendants of distant civilizations, long after Earth is gone. Yet the smudge carries all of that within its faint glow. It holds more future than present. Knowledge brings a kind of stillness. The universe becomes less like a backdrop and more like a living structure with its own trajectory. The Milky Way is not a fixed identity. It is a temporary arrangement of stars. Andromeda is the same. Together, they will become something new. The merger will erase familiar forms and create others. In time, the separate names may disappear. So the hook is set. A faint blur reveals a galaxy. A galaxy reveals a future. And the future asks you to look again at what you think you know about the night sky. To understand what is coming toward us, we first have to replay the night the universe admitted Andromeda was another world, not our cloud. The observatory dome creaked as it rotated, slow and heavy in the cold. Inside, a single telescope waited at the center, like an eye preparing to open. It was long after midnight. The mountains below were dark except for a few trembling lights in distant valleys. The astronomer on duty stepped to the eyepiece and steadied his breath. Clouds had cleared an hour earlier and the sky was finally stable. Tonight he was not hunting planets or comets. He was hunting clarity. He wanted to know whether the smudges that dotted the photographic plates were small clouds inside the Milky Way or something far larger. Before he placed his eye to the instrument, he studied the printed coordinates clipped to the stand. The object of interest sat in a predictable position, rising through the dark like a piece of lint caught on the sky. Observers of earlier centuries had called it a nebula. They assumed it was part of the Milky Way, a drifting clump of mist, a shred of gas that belonged to our own spiral. The idea that it might be another galaxy was considered extravagant. How could there be more than one galaxy if ours filled the entire heavens? The Milky Way was supposed to be the full extent of everything. The telescope tracked the spot precisely. A faint oval materialized, brighter near its core, dimmer at its edges. It did not behave like a local cloud. clouds shift quickly. They blur, reform, and vanish. This object held its shape from one year to the next. It rotated so slowly that only careful measurements could reveal the motion. Its brightness patterns suggested structure, not drift. Yet none of those clues provided distance. A local cloud and a remote galaxy could both look hazy. The difference between them was scale, and scale was locked behind light. This was the heart of the problem. A photograph could show details, but those details could not reveal how far away the object was. The night sky misleads the senses. A bright star could be close or enormous. A dim patch could be small or monstrously far. For astronomers in the early 20th century, Andromeda lived in a realm of ambiguity. Every plate held evidence that invited two interpretations, and the correct one depended entirely on distance. Until someone solved that puzzle, no one could claim that Andromeda was an island universe. The tension built over decades. Astronomers argued at conferences. They published claims and counterclaims. Some insisted that the Milky Way contained everything. They believed that the spiral patterns captured in photographs were swirling regions of gas inside a single enormous galaxy. Others suspected that those spirals were entire galaxies themselves, separate systems with their own stars, planets, and histories. If these spirals were other galaxies, the universe was unimaginably vast. If they were local clouds, the universe was still small and centered on us. The stakes were enormous. The very scale of existence was on trial. Inside the observatory, the astronomer pulled back from the eyepiece and examined the plate storage cabinet. Rows of glass sheets, each labeled with dates and coordinates, waited like silent witnesses. Many plates showed the same blurry oval. A few contained subtle bright points within the blur. Those points varied in brightness from one plate to another, to an untrained eye. They might seem like dust or defects. To someone with the right knowledge, they were clues. Stars that change brightness rhythmically behave like cosmic beacons. They act as distance markers. If one of them existed inside the blur, the universe would finally provide a ruler. Night after night, observers scanned those plates. They traced the light curves of the variable stars trapped within the haze. These were not binary systems blinking by chance. They were pulsating stars, whose periods of brightening and dimming encoded their true luminosity. Once those periods were measured, the distance would no longer be a matter of debate. The faint oval would either become a local cloud or a distant galaxy. Decades of argument would collapse into a single number. A breakthrough came when one observer noticed that the coordinates of a particular brightening point matched across several plates. Its rhythm was unmistakable. It brightened and faded in a steady pattern. Its peak brightness was known from studies of similar stars. By comparing the true brightness to the apparent one, the observer calculated the distance. The answer was far larger than any distance inside the Milky Way. The object could not be a cloud within our galaxy. It was a whole galaxy on its own. So the smudge on the sky was not a piece of the Milky Way, but a separate star city floating far beyond the reach of our spiral arms. It contained its own clusters, its own dust lanes, and its own populations of ancient and young stars. This realization shattered the old cosmic map. The universe became larger by orders of magnitude. Human understanding shifted in a single step. The night sky was full of other galaxies. The Milky Way was not the universe. It was only one of many. Think about that moment. A single calculation changed the scale of everything. The world did not feel different underfoot. Mountains did not shake. The air did not thin. But the mental landscape expanded. Humanity moved from living in a small cosmic city to living in a universe filled with countless cities. Andromeda became our nearest large neighbor. No longer a cloud, but a luminous metropolis across a vast gulf of space. The deeper meaning settled slowly. If the smudge was a galaxy, then the universe was not centered on the Milky Way. Our home was one of many structures. Our star was one among billions. Our story unfolded inside a much larger container than anyone had suspected. This did not diminish the human experience. It enriched it. Instead of a small stage, we inherited a vast one. Instead of a single island, we encountered an archipelago of galaxies with stories older than imagination. What else did the discovery imply? If Andromeda was a galaxy, it had its own gravitational field, its own motion, and its own fate. Astronomers measured its velocity using the spectra of its stars. The lines shifted. The shift revealed motion, not away, but toward us. This was unexpected. Most galaxies retreat as the universe expands. Andromeda moved against that flow. That meant the Milky Way and Andromeda were not drifting apart. They were drifting together. The discovery that expanded our universe also revealed a collision far in the future. To the astronomers who lived through this shift, the universe felt newly alive. It was no longer a static vault of stars. It was a dynamic landscape where galaxies moved through time, collided, merged, or faded. Andromeda was not just a distant curiosity. It was a key to understanding cosmic structure. It was proof that the Milky Way was not alone. Stand again in the mind's eye at the observatory. Imagine the observer pulling back from the telescope and looking at the valley lights below. They would not have heard any sound from the sky. Nothing in their surroundings hinted at the magnitude of what they had uncovered. Yet in that quiet room, the scale of the universe had transformed. Their calculations would travel through journals, conversations, and lectures. In time, school children would learn that the universe held billions of galaxies. The idea would become ordinary, but the night of its discovery was anything but ordinary. A final question lingers. If a simple smudge could reveal an entire galaxy, what other truths remain hidden in plain sight? Astronomers learned that the sky holds layers of meaning, and that understanding those layers requires patience, technique, and the courage to challenge old assumptions. The smudge became a symbol of that courage. Once we accepted Andromeda as a separate galaxy, the next question was simple and unsettling: what kind of giant had we just invited into our map? The first time you see a deep exposure of Andromeda, you notice the bright core and the long arms sweeping outward. That is the familiar face of a spiral galaxy. But when astronomers began pushing their instruments deeper, using long integrations and wide fields of view, they discovered that the visible disk is only the beginning of the structure. Around Andromeda sits a vast halo, an immense sphere of stars, gas, an unseen mass that stretches far beyond the graceful arms. If the bright disk is the recognizable city, the halo is the countryside, the ruins, and the foundation all at once. The halo does not shine in an obvious way. It looks faint and ghostly. To detect it, astronomers must gather enormous amounts of light and carefully filter out noise. Long ago, they thought the halo was sparse. Newer surveys revealed that it is far richer, full of old stars, shredded remnants of smaller galaxies, and paths of debris left behind by ancient collisions. The halo holds clues to Andromeda's history, the way a cliff face holds layers of rock. Each band in the cliff records a different era. Each shell in the halo carries the memory of a merger, an encounter, or a burst of star formation. Imagine slicing Andromeda like an onion. The bright disk is only the surface layer. Beneath it lie regions that contain stars older than any on Earth. Those stars drift slowly, held together, not by the visible matter, but by something much heavier and invisible. Observations reveal that Andromeda's outer regions rotate too fast for the gravity of the visible stars to hold them. Something else must be supplying the missing mass. That missing mass forms a giant halo of dark matter, a structure that outweighs everything you can see. The dark matter halo defines the shape of the galaxy's gravitational well. It extends hundreds of thousands of light years in all directions. If you could see it directly, it would not resemble the luminous disk. It would be a massive sphere that encloses the galaxy like a transparent shell. Visible stars orbit inside this shell. The halo's mass determines how fast stars move and how tightly the galaxy holds together. Without the halo, the disk would unravel over time. Whenever astronomers map the motion of stars in the outskirts of Andromeda, they see a pattern. The stars behave as if they are part of a larger structure. Even when the visible matter becomes thin, the stars remain bound. That binding is a sign of the dark matter halo. Measuring these motions is like watching leaves drift on a lake. The behavior of the leaves reveals the presence of deep currents that you cannot see. The stars in Andromeda's halo reveal the hidden gravitational currents around them. In the last decade, deeper imaging has shown that the halo is not smooth. It is full of streams and arcs. These structures formed when Andromeda consumed smaller galaxies. Over time, the smaller galaxies stretched into long ribbons of stars. Some of these ribbons circle the galaxy in loops. Others plunge inward toward the disk. Each stream marks a collision that happened long ago. Andromeda's halo is a graveyard of galaxies, and each remnant carries a story of destruction and absorption. The halo also contains star clusters. These clusters are dense spheres of ancient stars tightly bound by gravity. They orbit more from the central disk. Some clusters formed within Andromeda. Others belong to smaller galaxies before Andromeda absorbed them. They survive the mergers because their bond is strong. These clusters act as preserved pockets of history. Each cluster contains the chemical fingerprints of its birth environment. By studying those fingerprints, astronomers learn where the cluster originally came from. Consider one such cluster drifting on the edge of the halo. If you lived on a world inside it, your night sky would be filled with old red and yellow stars packed close together. The disk of Andromeda would appear as a faint glow across part of the sky. Every night you would watch the slow motion of the larger galaxy, a reminder that your cluster was once part of something else. You would inhabit a fragment of a long-lost system, preserved like a single room from a demolished house. The halo is not only stars and clusters, it also contains gas, mostly hydrogen. This gas is sparse but important. It supplies material for future star formation. Ultraviolet surveys show that Andromeda's halo is filled with gas hotter than the surface of any planet. This gas flows toward the disk over long timescales. Some of it escapes. Some of it drifts outward. The halo acts as both reservoir and boundary. It shapes how the galaxy evolves. Then there is the dark matter. It does not emit light. It does not reflect or absorb in any way that our instruments can detect. Yet its presence is undeniable. When astronomers plot the speeds of stars at various distances from the center, the curve of those speeds refuses to drop as expected from visible mass alone. Instead, the curve stays high. The stars act as if they feel the pull of a massive structure surrounding them. The halo's invisible weight provides that pull. At its core, the halo is the skeleton of the galaxy. Andromeda's disk hangs upon it. The motion of every star, cluster, and cloud is shaped by the halo's mass. The visible and invisible are bound together. When you think of Andromeda, you might imagine the beautiful spiral. But the halo is the true outline of the system. It is the deepest layer of the structure, the part that defines how the galaxy holds itself together. Why does this matter? Because the halo tells the story of how galaxies grow. Every merger, every encounter, every swallowed satellite leaves its mark in the halo. The disk shows the galaxy as it looks now. The halo shows what the galaxy has done. It records the ancient interactions that shaped the system into its present form. Without the halo, we would have only a partial picture of Andromeda's life. What questions rise from this? How many small galaxies did Andromeda absorb? How often do such collisions happen? Are we watching Andromeda in the middle of a long feast or at the end of one? If the halo contains clues to Andromeda's future, can we use those clues to predict its merger with the Milky Way? The halo's structure suggests that Andromeda has experienced many collisions. If that is true, the upcoming merger with our galaxy might follow familiar patterns. But if the halo contains unexpected features, the outcome could be stranger. There is also the question of symmetry. Does the halo form a perfect sphere? Some evidence suggests it is lopsided. Streams appear more densely on one side than the other. Certain clusters are grouped in patterns that hint at past impacts. The uneven distribution raises the possibility that Andromeda's past was more turbulent than we thought. A lopsided halo implies a lopsided history. Imagine a map of the halo laid across a table. The central disk sits in the center like a bright coin. Around it, faint lines trace the orbits of clusters and streams. Beyond them lies the dark matter halo, invisible but necessary. If you traced every orbit, you would reveal a complex dance. Some paths loop gracefully, others twist in long ellipses. Each path tells you something about the mass hidden beneath it. When astronomers simulate the halo, they do not draw its shape directly. They model the motions of stars and see what distribution of mass could cause those motions. The dark matter halo is the simplest explanation. It fits the data, but uncertainties remain. Some alternative theories suggest modifying gravity itself. Others propose that dark matter has properties we have not yet measured. The halo is both known and unknown. It is mapped by inference rather than observation. Still, the evidence points clearly to a halo far more massive than the disk. The majority of Andromeda's weight lies outside the region where its stars shine. The brightest part of the galaxy is only a small fraction of the whole. This idea can be unsettling. We are used to thinking of what we see as the main event, but in galaxies, the visible is only the surface. Most of the story lies in the unseen. Think of the halo as the deep foundation of a city. Buildings rest upon it. Roads curve according to it. People move through patterns shaped by the land beneath their feet. Yet most citizens never see the foundation. They know the city by its lights and architecture, not by the bedrock. Andromeda's visible disk is the lit portion of the city. The halo is the bedrock. Human scale helps clarify this. Suppose you lived in a world on the far edge of Andromeda's disk. Your sky would show the halo as a faint scatter of ancient stars, almost like a mist of distant lamps. You would not see the dark matter, but you would feel its influence. Your sun's orbit would follow the halo's gravitational path. Your world would be part of a massive structure you could not witness directly. Why does any of this matter to us? Because the Milky Way has a halo too. And understanding Andromeda's helps us understand our own. The upcoming merger will not be a simple blending of two disks. It will be a collision of two halos. Their shapes, masses, and histories will determine how the stars mix. The future of the night sky depends on structures we cannot see. These insights set the stage for the next question. If the halo reveals Andromeda's foundations, then what stories do its chemical fingerprints tell about the stars that inhabit those foundations? When we examine the chemistry of the halo's stars, we begin to learn not just how the galaxy is shaped, but how it lived. The deeper you look into Andromeda, the more you discover that its stars carry memories. Not memories in the human sense, but patterns written in the atoms that compose them. Every star is a chemical diary. Its composition reveals when it formed, what kind of environment surrounded it, and what earlier generations of stars lived and died nearby. When astronomers began to examine Andromeda through this lens, they uncovered evidence that reshaped the understanding of its past. The galaxy was not a simple spiral. It was a mosaic of stellar lineages, some native, some imported, some so unusual that they forced observers to rethink how galaxies grow. Chemical forensics begins with starlight. A star's spectrum is a rainbow broken into thin lines. Those lines are fingerprints of the elements inside the star: hydrogen, helium, oxygen, magnesium, iron. Each element absorbs light in specific ways. When astronomers collect this light and spread it into spectra, they can read those patterns with the precision of a forensic investigator examining clues at a crime scene. The trick is not in detecting the elements, but in interpreting their ratios. Those ratios reveal how enriched the star is. A star born early in the universe has few heavy elements. A star born late has many. Heavy elements accumulate as stars live and die, forging new atoms and scattering them through the galaxy. Across Andromeda, This chemical layering is not uniform. Some regions are rich in metals, others are metal poor. The variation is not random. It traces the paths of ancient events. Regions near the core tend to have higher metallicity because star formation was intense there for long periods. Outer regions often have lower metallicity because they developed more slowly, but the halo contains the strangest patterns. Many halo stars have chemical signatures that do not match those of the core or the disk. Their patterns resemble stars from much smaller galaxies. This suggests they were not born in Andromeda at all. They were carried in during mergers. Imagine opening a drawer in a library and finding books written in different alphabets. Some alphabets belong to the region. Others come from distant cultures. The halo of Andromeda is that drawer. Its stars come from many different origins. Each star carries a chemical alphabet that reveals its birthplace. When astronomers mapped these variations, they realized that Andromeda's outer regions were built from the remains of many smaller galaxies. Those galaxies arrived over billions of years, merged, and dissolved. Their stars now drift in wide orbits. Some cluster together. Others form streams that loop around the galaxy. Their chemical fingerprints match the histories of their lost homes. The central bulge of Andromeda tells another story. Chemical measurements show that the stars there formed in a rapid burst. They contain high levels of heavy elements. That means Andromeda's core went through intense cycles of star birth and death. Massive stars lived short lives, ended in explosions, and seeded the region with heavier elements. The process repeated until the core became a hub of chemically enriched stars. This does not mean the core is more advanced. It means it is older and more processed. Heavy elements are the ashes of past generations. The bulge holds the ashes of many. The disk is more complex. It contains both old and young stars. Some regions show high metallicity, while others show lower values. This variation indicates that star formation in the disk was not uniform. It surged, slowed, revived, and shifted over time. Streams of gas from the halo fed the disk intermittently. Collisions with smaller galaxies disturbed it, compressing clouds and triggering star formation. As a result, the disk of Andromeda is a patchwork of ages and chemical environments. It is neither pristine nor uniform. It is a living structure influenced by the events around it. Then come the rare stars. These stars stand out because their chemical patterns are unlike those of the rest of the galaxy. Some have extremely low metallicity, suggesting they formed soon after the early universe cooled. These stars are fossils of the first generation that followed the cosmic dark ages. If you were to stand on a world orbiting one of them, you would be near a stellar ancestor older than most galaxies' disks. Other rare stars show ratios of elements that suggest they formed in dwarf galaxies with unusual enrichment histories. Those dwarfs no longer exist. They were torn apart and absorbed by Andromeda, but their stars still carry the record of their extinction. A few stars exhibit patterns that are even more peculiar. They contain an excess of elements formed through specific nuclear reactions that do not occur commonly. These signatures act like stamps from exotic environments. Some arise in rare types of supernovae. Others form in binary systems where one star transfers material onto another. These rare stars are scattered like clues throughout the halo. They suggest Andromeda's past included unusual events. They hint that some stars lived violent lives before settling into the calm drift of the halo. To put this in human terms, imagine walking through an ancient city built over the ruins of many earlier towns. You find pottery shards from one culture, inscriptions from another, and metal tools from yet another. Each discovery reveals a layer of the city's history. Some layers match the patterns you expect. Others surprise you. The chemical forensics of Andromeda work the same way. Each star is an artifact. Each spectrum is a shard. Together, they reveal a history far more intricate than a simple spiral galaxy would suggest. Why does any of this matter? Because the chemistry of the stars tells us how galaxies evolve over time. The presence of foreign stellar populations proves that Andromeda grew by consuming other galaxies. It did not grow only by forming its own stars. It grew by absorbing neighbors. This means its future merger with the Milky Way will produce a galaxy that carries the chemical fingerprints of many lineages. The next generation of stars formed after the merger will inherit all those elements. This raises further questions. How many mergers has Andromeda undergone? Which of its rare stars came from collisions long forgotten? How much of the halo is composed of stars stolen from smaller systems? If the halo is a graveyard, how many graves does it contain? These questions guide astronomers as they attempt to reconstruct the galaxy's past. A major clue comes from the distribution of chemical signatures across the halo. Some regions contain stars with similar patterns, suggesting that they originated in the same dwarf galaxy. Other regions show mixed populations, indicating that multiple mergers overlapped. The amount of mixing reveals how long ago the mergers occurred. Stars from recent mergers remain tightly grouped. Stars from ancient mergers are more dispersed. There is also the matter of alpha elements, such as oxygen and magnesium. These elements form in the cores of massive stars and are released by certain types of supernova. When astronomers measure the ratios of alpha elements to iron in Andromeda's stars, they identify patterns. High ratios indicate rapid star formation. Lower ratios suggest slower histories. By measuring these ratios across the galaxy, researchers reconstruct the timeline of Andromeda's early growth. They find that Andromeda formed stars vigorously at times and slowly at others. It had active eras driven by fresh gas inflows and quieter eras when star formation waned. One of the most striking discoveries is the existence of stars that appear older than most stars in the Milky Way. These stars are extremely metal-poor. They likely formed before Andromeda became a spiral galaxy. They belong to the earliest structures that collapsed after the universe cooled. Studying them reveals how galaxies first assembled. They are the closest we can get to observing the early universe through the lens of a nearby system. Human scale again helps. Picture holding an old coin. Its surface is worn. Its markings are faint. Yet it carries the weight of its age. It represents a time long before you lived. Rare stars in Andromeda are like that coin. They carry the imprint of cosmic eras long past. When astronomers decode their spectra, they read the history of the universe itself. But chemical clues also hint at surprises. Some regions show enrichment patterns that do not match current models. They contain unexpected combinations of heavy elements. These signatures could point to events not yet understood. Perhaps Andromeda hosted rare types of supernova explosions. Perhaps it absorbed dwarf galaxies with unusual enrichment histories. Or perhaps the models of chemical evolution need revision. These questions remain open. The chemical forensics of Andromeda continue to challenge assumptions. There is also the possibility of stars formed from gas ejected during past mergers. When galaxies collide, gas is stripped from their disks. That gas can cool and form new stars in unexpected places. If those stars form in the halo, they inherit chemical patterns that differ from both original galaxies. This makes them difficult to classify. Their existence complicates the reconstruction of mergers. They are the wild experiments of cosmic history. Consider another layer. Some stars show evidence of process enrichment. This means they contain elements formed in long-lived stars that released material slowly. Others show process enrichment, formed in rapid nuclear events such as neutron star collisions. The distribution of these types of stars reveals which regions of Andromeda experienced calm star formation and which experienced explosive events. The galaxy becomes a map of quiet and violent epochs. Why do these details matter for the bigger story? Because chemical forensics link directly to the upcoming merger with the Milky Way. When the two galaxies collide, their stars will mix, their chemical histories will combine. The result will be a new galaxy with a composite identity. Understanding Andromeda's chemical past helps predict which regions will merge smoothly and which will form chaotic patterns. It also helps identify which stars will reveal their origins long after the merger. This leads to one final reflection. The stars of Andromeda carry more than light. They carry history. Each spectrum is a clue. Each chemical ratio is a phrase in a much longer story. To read that story is to see Andromeda not as a simple spiral, but as a layered structure shaped by countless events. Its halo, its disk, and its core are the chapters of that story. Its rare stars are the footnotes that challenge the easy interpretation. The chemistry hints at unusual stars, but to meet Andromeda's strangest residents, we have to walk into its rare stellar neighborhoods. The deeper the surveys of Andromeda became, the more the galaxy resembled not a single organized system, but a collection of scattered families. Its star clusters drift through old orbits like tight-knit villages. Its stellar streams trail behind them like the broken roads of vanished towns. Even the halo, sprawling and dim, contains the signatures of long-lost lineages. If Chapter 3 revealed that Andromeda's stars carry chemical memories, then Chapter 4 reveals the geography of those memories. It shows that the galaxy is not built from a continuous line of ancestry. It is built from fragments. Clusters are the first clues. Many are globular clusters, dense spheres of ancient stars bound tightly enough to survive for billions of years. They orbit far from the bright disk, some with slow, sweeping paths, others cutting in close before drifting outward again. These clusters formed early in the galaxy's life, or were captured from smaller galaxies that Andromeda absorbed. Their chemical signatures, motions, and ages vary. Some match the core, others match the disk, but many do not belong to any familiar family. They came from elsewhere. Imagine holding a handful of marbles. Some have similar patterns and colors. Others look completely different. The globular clusters of Andromeda are the marbles. If you sort them by pattern, you discover that the galaxy is made of many imported pieces. Observers found clusters with orbits tilted relative to the disk, clusters moving faster than expected, clusters streaming along unusual paths. Each anomaly pointed toward a missing parent galaxy. Over time, a picture emerged. Andromeda built its halo by consuming smaller systems. Their clusters survived the encounter and now drift freely, like rooms preserved from demolished buildings. The streams are even more striking. When a small galaxy falls into a larger one, gravitational tides stretch it into a long ribbon of stars. These ribbons loop around the host galaxy in wide arcs. Some wrap around multiple times. Some descend toward the disk, then swing back out. They are bright enough to detect with long exposures and stable enough to trace across large portions of the sky. They represent the bones of long-devoured galaxies. Early digital surveys revealed the first of these streams. Later, more powerful instruments uncovered more. One stream, wide and pale, cuts across the halo like a diagonal scar. Another twists around Andromeda in an elegant arc. Each stream contains stars with similar chemical signatures. These signatures match those of dwarf galaxies, rather than the core or disk. The conclusion became unavoidable. Andromeda's halo is a graveyard of galaxies. Its streams are the paths of ghosts. What? The presence of so many streams forced astronomers to reconsider the scale of Andromeda's past. How many galaxies did it absorb? How often did mergers occur? Some simulations suggest that Andromeda may have consumed a massive satellite billions of years ago, an event so large that it reshaped the entire halo. Other models propose a steady influx of small galaxies over time. Either way, the evidence lies in the broken family tree. Each stream is a branch snapped from a parent galaxy. Each cluster carried by that stream is a surviving leaf. To understand the full picture, scientists study the orbits of the clusters and streams together. When they plot those orbits, patterns emerge. Some streams align with specific cluster groups. These alignments suggest that the clusters once lived inside the dwarf galaxies that created the streams. When the dwarfs were torn apart, the clusters were freed but retained their original paths. Their shared motion reveals a common past. By grouping clusters based on their orbits, astronomers can reconstruct which clusters belong to which long-lost systems. Think of it like discovering old migration routes carved into a continent. If you map the paths of ancient travelers and match them with artifacts left behind, you can identify which groups traveled together. Andromeda's halo works the same way. The clusters and streams mark the roots of galaxies that no longer exist. Their combined orbits tell a story of collisions, captures, and erosion. The disk of Andromeda, though calmer today, also carries evidence of past impacts. Some sections show distortions that hint at past encounters. These distortions are subtle, like wrinkles in a stretched fabric. They arise when smaller galaxies pass near the disk. Their gravity pulls on the gas and stars, leaving behind ripples. These ripples can trigger bursts of star formation. Some of the bright blue clusters in Andromeda's disk likely formed during such episodes. Their chemistry and age align with periods when satellite galaxies passed through. Why do these details matter? Because they reveal the mechanisms through which galaxies grow. The Milky Way has its own streams and its own broken family tree. But Andromeda offers a clearer view because many of its streams are brighter and easier to trace. Studying Andromeda shows that large galaxies are not solitary structures. They are ecosystems that thrive on interactions. They grow by absorbing smaller neighbors. Each absorption reshapes the larger galaxy. Over billions of years, these events accumulate into a mosaic. One of the most surprising discoveries came from mapping the planes of satellite galaxies around Andromeda. Instead of being scattered at random, many of Andromeda's satellites lie in a thin, rotating plane. This structure is difficult to explain. It could be the result of a major ancient merger. It could reflect an unusual pattern in the distribution of dark matter. Or it could be a temporary arrangement that will dissolve over time. Whatever the cause, it suggests that Andromeda's history contains large-scale events we do not yet fully understand. Some satellites show signs of being shredded. Their edges are faint and stretched. Their stars spill outward. Others appear surprisingly intact, perhaps because they have only recently begun to fall inward. The combination of intact satellites and shredded remnants paints a vivid picture. Andromeda's halo is not static. It is an active region where galaxies are either approaching dissolution or carrying the marks of previous encounters. Human scale helps again. Imagine walking through an archaeological site where the ruins of many cultures lie mixed together. Stone walls from one era overlap with roads from another. Potsherds from different villages lie side by side. If you map the layers, you uncover a history of migration, conquest, and assimilation. Andromeda is that archaeological site. Its halo is the excavation. Its clusters and streams are the ruins. Why is the history so fractured? Because galaxies evolve through repeated interactions. They do not form in isolation. They grow through accretion. They attract small companions. They collide with comparable galaxies. Each event leaves a trace. Those traces accumulate into a broken family tree. Some branches remain visible. Others have crumbled. But the outline remains clear. Andromeda's past is not linear. It is branching and tangled. The chemical signatures discussed in Chapter 3 confirm these patterns. Streams often contain stars with low metallicity, consistent with origins in small galaxies that formed early. Clusters carried by these streams show similar compositions. Their shared chemistry reinforces the orbital evidence. Together, they reveal that Andromeda's halo is full of ancient debris. Moreover, the distribution of these features hints at major events. If Andromeda once absorbed a large satellite galaxy, the debris from that event would spread across a wide region. Some simulations indicate that the halo's asymmetry could be due to such an event. A massive merger billions of years ago could have tilted the halo, introduced streams, and reshaped the disk. If that model is correct, Andromeda's outer regions are still settling into equilibrium. This raises a question. How does the history of past mergers shape Andromeda's future? If the halo is lopsided, the upcoming merger with the Milky Way might be more dramatic on one side than the other. Regions filled with debris could be stirred violently. Other regions might merge more smoothly. Understanding the halo's asymmetry helps predict the shape of the future Milky Way-Andromeda union. At its core, Andromeda's broken family tree is a record of survival and loss. Smaller galaxies fell inward. They were torn apart. Their stars were scattered, but their clusters survived. Their streams survived. Their chemical signatures survived. These remnants allow astronomers to rebuild the past. They also show that galaxies like Andromeda are not monolithic. They are built from many lineages. If you could stand on a world inside one of the streams, the night sky would reveal your history. You would see the disk of Andromeda stretching across the sky. You might see other streams faintly, like pale arcs. You would not know that your ancestors came from a different galaxy, but your star would carry that fact in its composition, and your orbit would trace it in space. These ideas lead to another reflection. The Milky Way and Andromeda will merge. Their clusters, streams, and lineages will mix. The new galaxy will inherit both family trees. Some clusters will survive intact. Others will be drawn into new orbits. The streams will twist and fold. The family tree will become even more complex. The wandering towns and torn streams show us where Andromeda has been, but something far heavier is steering all of them. The bright arms of Andromeda draw the eye first, but the deeper truth of the galaxy hides in places where light fails. At its center sits a silent mass that outweighs millions of suns. Around it stretches an immense halo of unseen matter. These two structures, one compact and one vast, shape how the galaxy moves, breathes, and evolves. If the visible stars form the architecture of Andromeda's luminous city, then the black hole and the dark matter halo form the invisible frameworks that hold the city together. To understand where Andromeda has been and where it is going, you must learn to read what cannot be seen. The journey begins in the core. When astronomers look at the central region of Andromeda, they see a bright bulge of densely packed stars. Long exposures reveal two bright peaks near the center, as if the galaxy holds twin hearts. One of those peaks marks the location of a supermassive black hole. This black hole is quiet today. It does not blaze with the intense radiation of an active quasar. Instead, it sits in a calm state, swallowing little, shaping much. Its presence is known through the rapid orbits of nearby stars. Those stars move with speeds that only a massive object can produce. To measure the black hole's mass, astronomers observe the Doppler shifts of stars near the core. As the stars move, their light stretches and compresses. These changes reveal their velocity. When the velocities are plotted, the pattern shows that the stars are responding to a concentrated mass. The mass fits the profile of a black hole millions of times heavier than the Sun. It is smaller in mass than the black hole at the center of some giant galaxies, yet heavier than the one at the heart of the Milky Way. What does this difference mean? It suggests that Andromeda's history involved periods of intense feeding, followed by long, calm intervals. Picture the core as a city built around a dormant volcano. When the volcano is active, its glow affects everything around it. When the volcano rests, the city lights dominate. In the distant past, Andromeda's core may have blazed with activity. Gas spiraled inward. Radiation streamed outward. Now the black hole is quiet. The surrounding stars shine more brightly than anything the black hole emits. But the structure remains. The volcano may be dormant, but it is still the deepest anchor of the city. The influence of the black hole does not extend far from the core, a few light years out. The stars feel the pull of the entire bulge, a few thousand light years out. The disk and spiral arms dominate. Far beyond that, another invisible architecture rises. This architecture is the dark matter halo. Unlike the black hole, the halo is not concentrated. It is diffuse and enormous. Its gravitational pull shapes the orbits of stars, clusters, and streams across the galaxy. Astronomers discovered the halo by studying the rotation curve of Andromeda. When they measured the speed of stars at different distances from the center, they expected the speeds to decrease with distance. That is what happens in systems where most of the mass lies near the center. But in Andromeda, the speeds do not drop. They stay high. This behavior implies that a large amount of mass lies outside the visible disk. The mass extends outward into the halo, It pulls on the stars, keeping their speeds elevated. If you imagine the galaxy as a giant amusement ride, the visible stars represent the seats. The dark matter represents the massive support structure hidden beneath the floor. The riders feel the effects of that structure even though they cannot see it. In Andromeda, the support structure is far heavier than the seats. This means that most of the galaxy's mass is invisible. The halo also shapes how satellites orbit Andromeda. Many of its smaller companion galaxies move in elongated paths. Their motions do not match the expected patterns of a galaxy dominated by visible matter. The halo's gravity pulls them harder than the luminous mass alone would predict. Some satellites follow orbits that plunge inward, then swing back out. Others circle in the strange plane discussed in the previous chapter. All are influenced by the halo's unseen weight. Dark matter cannot be seen directly. It does not interact with light, but astronomers detect it through gravitational effects. They also infer its presence through the distribution of hot gas in the halo. The gas temperature is too high to be held by visible mass alone. Only a massive halo can keep that gas from escaping. This adds further evidence that dark matter dominates Andromeda's structure. Why does this matter? Because dark matter shapes how galaxies form and evolve. Without it, the early universe would have remained smooth. Gravity from dark matter pulled gas into clumps. Those clumps became the seeds of galaxies. Andromeda grew within one of those clumps. Its halo formed long before its disk. The halo guided the inflow of gas that created the spiral arms. It directed the paths of satellite galaxies. It shaped every major event in Andromeda's life. The core and the halo form a hierarchy of invisible influence. The black hole controls the inner few light years. The bulge controls the next 1,000. The disk and spiral arms control the next tens of thousands. Beyond that, the halo dominates. This hierarchy reveals that galaxies are layered systems. Visible light tells only part of the story. Gravity reveals the deeper structure. There are mysteries within this structure. The dark matter halo does not appear perfectly smooth. Simulations predict that halos should contain many small clumps of dark matter. Some of these clumps might host faint satellite galaxies. Others might float unseen. If these clumps exist, they could affect the paths of streams. They could distort the orbits of clusters. They could leave small signatures in the distribution of stars. Observers search for these effects. Some hints appear, but the full picture remains incomplete. Another mystery concerns the alignment of the halo. If Andromeda experienced a major merger in the past, the halo may be tilted. Its mass may not be centered perfectly on the disk. This tilt could explain some of the asymmetries seen in the streams. It could also affect how Andromeda will merge with the Milky Way. A tilted halo creates uneven gravitational pull. When two galaxies collide, such asymmetry influences the paths of their stars. It shapes the final form of the merged galaxy. The black hole raises additional questions. If Andromeda once had an active quasar phase, when did it happen? What triggered it? Why did it end? Could it flare up again during the merger with the Milky Way? Black holes become active when gas flows inward at high rates. Collisions between galaxies can funnel gas toward the center. During the upcoming merger, such a funneling might occur. If it does, Andromeda's black hole could shine again. It could become a beacon bright enough to outshine the combined disks. There is also the matter of the twin peaks in the core. One interpretation is that the peaks are not dual black holes, but rather a single black hole surrounded by an eccentric ring of stars. The ring's orbit causes the light distribution to appear double. This structure is stable but unusual. It hints at past events that disturbed the core. Perhaps a smaller galaxy passed close enough to warp the central region. Perhaps a previous merger funneled stars inward. The core's structure is a fossil record of those events. Human scale helps again. Imagine standing near the center of a great city. Two bright towers dominate the skyline. They do not belong to separate districts. They belong to the same complex. Their presence reveals that the city has grown through expansions and renovations. The central region of Andromeda is a cosmic version of such a complex, shaped by events that occurred long before humanity existed. Why does the invisible architecture matter to us? Because it determines the fate of the Milky Way. When the two galaxies meet, their halos will collide first. The halos are far larger than the disks. Their invisible masses will interpenetrate, causing stars to shift into new orbits. The visible collision will be slow and graceful, but the invisible collision will be immediate and powerful. The halos will dictate the final shape of the merged galaxy. They will determine how stars mix, how gas flows, and where new stars form. All of this creates a final question. If the halo and black hole shape Andromeda so completely, what kinds of maps can reveal their influence? Astronomers use radio waves, optical spectra, infrared light, and X-rays to build layered maps of the galaxy. Each wavelength reveals a different piece of the structure, but none reveal the halo directly. Instead, the halo must be inferred from the movements of stars and gas. Mapping it is like mapping wind by watching leaves move. These invisible influences prepare the way for the next step. If we can map the dark matter and track the black hole's influence, then we can also map how Andromeda looks across the full spectrum of light. Once we can see that composite view, we can begin to ask where inside all this structure worlds and lives could exist. To understand Andromeda fully, you must learn to see it more than once. The human eye observes only a thin slice of reality, a narrow band of visible light that reveals little beyond the luminous stars and bright dust lanes. But a galaxy is not a single picture. It is a layered structure, each layer visible only through a different window. When astronomers map Andromeda across the electromagnetic spectrum, they uncover a shifting architecture. Each wavelength adds a new sheet to a giant transparent diagram. Only by stacking all these sheets can you see the true outline of the galaxy. Start with the visible. In ordinary light, Andromeda appears as a broad spiral with a bright central bulge and sweeping arms. The dust lanes appear as dark streaks cutting across the disk. Star clusters sparkle faintly around the edges. This is the view most people picture, the view that inspired early drawings and photographs. But visible light tells only the story of stars hot enough and bright enough to shine through the interstellar medium. It hides as much as it reveals. Shift to ultraviolet and the picture changes. Hot, young stars blaze in ultraviolet wavelengths. These massive stars live short lives. They gather in star-forming regions. When Andromeda is observed in ultraviolet, the spiral arms glow with knots of newborn stars. These knots trace the regions where gas has recently collapsed into new clusters. The ultraviolet view is the map of youth. It highlights the places where the galaxy is still building. Now look in infrared. Dust absorbs visible and ultraviolet light, but it glows warmly in infrared. Observing Andromeda in infrared reveals the cold gas and dust that lie between the stars. It shows the raw material from which new stars will form. The spiral arms appear thicker in infrared than in visible light. Hidden structures emerge. The core shines strongly. The dust lanes become more transparent. In infrared, Andromeda becomes a quieter, softer shape, lit not only by starlight but by the glow of the materials that cradle future stars. Radio wavelengths reveal another layer. In radio maps, hydrogen clouds stretch far beyond the visible disk. These clouds trace the structure of Andromeda's outer disk and halo. They show where gas flows inward and where it drifts outward. They reveal warps, bends, and asymmetries. Observations of hydrogen allow astronomers to measure the rotation speed of the galaxy at great distances. These measurements provide some of the strongest evidence for the dark matter halo. Without radio wavelengths, the outer architecture of the galaxy would remain unknown. In X-rays, Andromeda becomes something else entirely. The brightest sources in X-ray images are often remnants of stellar explosions, binary systems where gas spirals onto compact objects, and hot gas surrounding the core. In X-rays, the calm spiral is replaced by a pattern of bright points scattered across the disk and halo. Each point marks an extreme environment. a place where matter is being torn apart or heated to extraordinary temperatures. These X-ray signatures trace Andromeda's violent episodes, its supernova remnants, and the energetic processes near its central region. Each wavelength has its own strengths, but no single one tells the truth alone. Astronomers learned this by overlaying maps. When they combined infrared maps with visible maps, the dust lanes aligned with voids in the starlight. When they layered ultraviolet maps over radio maps, they discovered that star formation often occurs near the edges of dense hydrogen clouds. When they placed X-ray maps over everything, they noticed that some bright points sit far from the visible disk. These points often mark the remains of ancient collisions or compact binary systems flung outward during chaotic events. Imagine the process as building a jigsaw puzzle where each piece is a different color. If you use only one color, the picture is incomplete. Only by assembling all colors together does the image emerge. Andromeda's multi-wavelength map reveals a galaxy that is both orderly and chaotic. The orderly part lies in the spiral arms, the bulge, and the broad disk. The chaotic part lies in the streams, the hot gas, the warps, and the high-energy events scattered across the halo. One of the most surprising features revealed by these maps is the extended disk of gas. Andromeda's radio profile shows that the hydrogen disk extends much farther than the visible disk. It twists and bends, creating a warped structure. This warp may have formed during encounters with satellite galaxies. It may reflect the shape of the underlying dark matter halo. Whatever the cause, it reshapes the understanding of Andromeda's outer boundaries. The galaxy is not a tidy spiral with a clean edge. It is a system with arms that continue far outward, shaped by forces that do not appear in visible light. Another feature that emerges under multi-wavelength mapping is the presence of faint rings. These rings appear in some infrared and ultraviolet images. They may represent waves of star formation triggered by past collisions. When a smaller galaxy passes through a larger one, it sends ripples through the gas. Those ripples compress material into ring-shaped structures. If Andromeda shows such rings, it suggests that a smaller galaxy plunged through its disk in the past. The rings become time markers, recording the moment of impact. The core also transforms across wavelengths. In visible light, it is a bright sphere. In infrared, it becomes even brighter, its heat revealing hidden structures. In X-rays, it becomes a cluster of energetic sources. Each wavelength shows a different layer of the core's architecture. Together, they reveal a region shaped by intense star formation, dynamic interactions, and the influence of the central black hole. If you mapped only the visible light, you would miss everything happening beneath the surface. Mapping across wavelengths also reveals how Andromeda interacts with its environment. Its halo contains hot gas detectable in X-rays. Its disk interacts with streams of cold gas visible in radio. Multi-wavelength maps show how these components flow. They reveal a circulation system, like a galaxy breathing. Gas flows inward, forms stars, gets blown outward by supernovae, cools, and returns inward. Without multi-wavelength mapping, this cycle would be invisible. Questions arise from these observations. How stable are the structures revealed in different wavelengths? Do the ultraviolet knots of young stars align with the long-term patterns shown in infrared? How does the distribution of hot gas compare with the distribution of dark matter? What role do collisions play in shaping the radio structures? These questions guide researchers as they refine models of Andromeda's evolution. Human perspective clarifies the importance of this approach. If you stand in a dark room and shine a single colored flashlight, you see only one version of the space. Shine a different color and different details appear. Shine lights across the spectrum and the full shape of the room emerges. Andromeda is a room 1,000,000 light-years wide. Only multi-wavelength mapping reveals its architecture. Why does this matter for the larger story? Because the upcoming merger with the Milky Way will unfold across all these layers. The gas seen in radio wavelengths will collide first. The dust seen in infrared will compress into new star-forming regions. The bright ultraviolet knots will flare where collisions trigger fresh star birth. The X-ray sources will multiply as compact objects interact in new ways. The visible disk will distort. The invisible halo will guide the paths of stars. If we wish to predict the future shape of the merged galaxy, we need to understand Andromeda in all wavelengths. A galaxy is not a flat picture. It is a stack of atmospheres, currents, and skeletons. Each wavelength reveals one part of the puzzle. Once we can map Andromeda in such detail, the next obvious question is where, inside all this, could worlds and lives actually exist? When people think of Andromeda, they imagine a distant spiral, grand but unreachable. Yet if you look closely at its stars, clusters, and reservoirs of gas, a stranger question appears. Could there be worlds inside Andromeda where life has taken hold? Could there be oceans circling suns we can barely resolve? Could the galaxy across the void carry its own civilizations? These questions cannot be answered directly, but the physics of stars, planets, and environments allows a careful examination. To explore Andromeda's potential for habitability, you must use everything learned so far, from cluster histories to chemical clues to multi-wavelength maps. The first obstacle is simple distance. Individual stars in Andromeda blur together. Even the most powerful telescopes cannot easily pick out Earth-sized planets around them. But planets need not be seen to be expected. Planet formation follows from the presence of heavy elements forged by earlier generations of stars. These elements build rocky planets, atmospheres, and complex chemistry. Andromeda's disk contains rich metals, more than enough to form planets. Its halo, though older and poorer in metals, still contains stars with small traces of heavy elements. The raw materials are present. In the disk of Andromeda, star formation has been active for billions of years. Many stars formed with compositions similar to those in the Milky Way. Wherever there are stars like the Sun, there is good reason to expect planetary systems. Surveys of our own galaxy show that planets are common. Most stars have at least one. Some have many. There is no reason to think Andromeda is different. Its disk likely hosts billions of planets, ranging from small rocky worlds to large gas giants. Some of those rocky worlds likely orbit within the habitable zones of their stars, regions where water could remain liquid. Habitability depends on more than distance from a star. It depends on stability. Stable environments require long-lived stars and calm neighborhoods. The inner disk of Andromeda is crowded. Supernovae occur more frequently there than in quieter regions. High radiation can strip atmospheres or sterilize surfaces, but farther out in the disk, conditions are more stable. Sun-like stars drift peacefully. Their planetary systems enjoy billions of years of relative calm. Life could arise and evolve on worlds in these regions. Then there are the clusters. Globular clusters contain ancient stars. The density of stars in these clusters is extreme. If a world existed in such a place, its night sky would be filled with hundreds of bright suns. But the close proximity of stars would pose risks. Gravitational interactions could disturb planetary orbits. Radiation exposure could be intense. Yet some theories propose that long-lived, low-mass stars and clusters might host stable planets in quieter regions of the core and outer halo. The environments would be strange, but not impossible. A world in a cluster might experience far more starlight than Earth ever sees. More unusual possibilities emerge in the streams. These long ribbons of stars, created by the ruins of absorbed galaxies, contain ancient stellar populations. Planets formed in these systems might have migrated into Andromeda through mergers. If so, any life on such worlds would have endured cosmic upheaval. Their skies would have changed dramatically over time. Yet even upheaval does not forbid habitability. If the planets orbit long-lived stars and retain stable orbits, life could persist. Chemical evidence suggests that Andromeda contains stars with a wide range of metallicities. Some are extremely metal-rich. Such stars could form planets with large rocky cores. Others are metal-poor, formed early in the history of the universe. Their planets, if they exist, might be smaller or rarer, but life does not require a galaxy uniformly rich in heavy elements. It requires only pockets of stability. Andromeda has many such pockets. To consider life in Andromeda is to imagine the scale of its diversity. Picture a world within one of its bright spiral arms. Its sky would show a dense field of stars, far brighter and more numerous than in our own. Its night would hold the glowing band of the disk, stretching from horizon to horizon. If its inhabitants developed telescopes, they would see the Milky Way as a faint streak across the void. They might call it a neighboring fog, a distant cloud. Their astronomers might argue for centuries about whether it is a small cloud within Andromeda or another galaxy. Their debates would mirror ours. But there are challenges. Planetary systems near regions with high ultraviolet radiation may struggle to maintain stable atmospheres. X-ray, bright sources in the core and outer disk pose further risks. Collisions between gas clouds during mergers may disrupt star-forming regions. Habitability is not uniform across a galaxy. It is patchy. It depends on time, location, and stellar type. Andromeda's disk, with its broad regions of calm star formation, is the most likely host of habitable worlds. The halo, sparse and ancient, is less likely but not impossible. Some halo stars harbor stable systems. Others drift alone without planets. There is another angle. If life arose in Andromeda, could its signals reach us? The vast distance makes detection extremely difficult. Radio signals decay as they spread. Light carrying spectral signatures of artificial structures can be lost in the noise of the galaxy. Even if a civilization sent beams of light across the void, their signals might be too faint by the time they reach us. Yet the absence of evidence is not evidence of absence. A civilization could exist in Andromeda without leaving detectable traces. Their messages, if they exist, may simply be too faint or too rare. Some astronomers have considered whether alien megastructures in Andromeda could be visible. Large structures that block starlight might create detectable dips in brightness. Infrared signatures might reveal massive energy harvesting systems. But so far, nothing conclusive has been observed. This does not rule out advanced civilizations. It only means that either they are rare, they are subtle, or they are beyond our detection methods. The galaxy is vast. Our observations cover only a fraction of its stars. Another question arises. How would a civilization in Andromeda see us? They might detect our Milky Way as a spiral galaxy. They might map our satellites. They might sense our rotation curve, but unless they have extraordinary technology, they would not see Earth directly. They would not know whether life exists here. Their questions would echo ours. What kinds of worlds exist across the void? What events shape their history? What lights fill their sky? Habitability also ties into the future. When Andromeda and the Milky Way merge, their planetary systems will drift through new gravitational fields. Some worlds will move into safer regions. Others may drift into zones with higher radiation. Some may be ejected into intergalactic space, becoming rogue planets. These rogue planets, though cold, could carry subsurface oceans heated by internal radioactivity. Life, if present, might survive even as the stars rearrange. The idea of worlds in Andromeda is not speculation for its own sake. It is a way of understanding what it means to live inside a galaxy. A galaxy is not only stars and gas. It is a stage for planets, climates, oceans, and potentially life. If Andromeda holds worlds like Earth, then the space between us is not just a void, but a separation between stories. Those stories could be as long as our own, or far older. Human scale brings the idea into focus. Stand on a shoreline at night. Look at the line of lights across the water. You cannot see the people who live there. You cannot hear their voices, but you know the lights represent lives. Andromeda is like that distant shore. We see the lights of its stars. We know nothing of the lives that may circle them, but the possibility remains. Quiet and steady. Why does this matter? Because the study of worlds in Andromeda is a study of context. It reminds us that the Milky Way is not unique. It is one galaxy among many. The questions we ask about our own origins extend outward. If life exists here, it may exist elsewhere. The physics is not unique to Earth. The chemistry is not unique to the Milky Way. The conditions for life are not limited to one galaxy. Yet a deeper question presses in. Could we ever reach those worlds? The distance makes travel with current technology impossible. Even light takes over 2 million years to cross the void. But the purpose of imagining worlds in Andromeda is not to plan a voyage. It is to understand that the universe is richer than the limits of our eyes. It is to grasp that planets and life may be common, even if unreachable. And so we end with a reflection. Andromeda is not only a giant spiral, it is a potential archipelago of worlds. Some may be barren, some may be vibrant, some may have skies filled with the glow of the disk, some may drift alone in silence. The galaxy is a stage for many possibilities. If such worlds can exist, the next step is uncomfortable. Could anyone, or anything, ever cross the darkness between us and them? To speak of traveling from the Milky Way to Andromeda is to imagine a journey across the largest frontier anyone has ever considered. The distance is more than 2 million light-years. It stretches beyond every familiar scale. It dwarfs the span of human history. It renders ordinary engines meaningless. Yet the question persists. If worlds exist in Andromeda, could anything ever cross the void between us? Could a probe, a vessel, or even a message make the journey? The simplest answer is that nothing powered by current technology can reach Andromeda within the lifetime of a civilization. But the full answer is more layered. It involves the physics of propulsion, the constraints of relativity, and the strange possibilities hinted at by theoretical physics. It also involves scale. To cross the void, you must build an idea that can survive ages. You must imagine a craft that outlives continents, oceans, and species. This is a test not of engineering first, but of patience. Begin with the most basic concept, a conventional rocket. Rockets carry fuel. Fuel has weight. To accelerate a craft to a meaningful fraction of the speed of light, the craft would require far more fuel than it could carry. Every calculation collapses under this weight. The rocket equation becomes a quiet verdict. Chemical rockets cannot cross the void. Even nuclear rockets fall short. Their speeds are too low. At those speeds, the journey to Andromeda would take hundreds of millions of years. Next, consider advanced propulsion methods that push closer to the limits of known physics. Fusion drives offer more promise. A craft powered by fusion could theoretically reach perhaps 10% the speed of light. At that speed, the journey would still take tens of millions of years, longer than ecosystems endure, longer than landscapes persist. A craft could drift through intergalactic space long after its designers vanished. It would arrive as an artifact from a species that no longer exists. The question becomes not whether the craft could be launched, but whether the meaning of the journey could survive its arrival. Light sail technology offers a different approach. Instead of carrying fuel, a spacecraft could ride on a beam of light. A powerful laser array could push a thin craft to a significant fraction of the speed of light. Concepts such as starshot probes are built on this principle. For journeys within the Milky Way, such probes could reach nearby stars in decades. But for a journey to Andromeda, even a craft traveling at 20% the speed of light would require more than 10 million years. The probe would leave behind a history that none of its creators could witness. Yet these ideas open another door. If a craft is small enough, simple enough, and durable enough, perhaps it does not need to endure in the way a human expedition would. It could be a seed of information, a machine designed to record and transmit data, an emissary that carries a message rather than a crew. If a civilization wished to explore galaxies, it might send such seeds across the void, knowing that the journey would outlast its own existence. The act of sending would matter as much as the arrival. This leads to a more speculative layer. Could a civilization send a self-replicating probe that builds new units from the materials it finds? Such probes could spread across a galaxy over millions of years. They could cross intergalactic space. If they existed, we might expect to see evidence, but no such evidence is known. Either such probes are rare, or civilizations do not build them, or they break down long before covering such distances. Even the most ambitious ideas face the quiet limits of entropy. Then comes the more exotic frontier, wormholes. These hypothetical tunnels in space-time appear in solutions to Einstein's equations. They could, in principle, connect distant regions of the universe. A wormhole between the Milky Way and Andromeda would shorten the journey to minutes, but wormholes require properties of matter not yet observed. They may not be stable. They may not exist in the forms imagined. Some theories suggest that microscopic wormholes flicker in the fabric of space. Others propose that large wormholes would collapse instantly. Without empirical evidence, wormholes remain a mathematical possibility rather than a practical path. Still, imagining them teaches something. If any civilization learned to manipulate space-time, the gulf between galaxies would no longer be an absolute barrier. The void would become a passage rather than a wall. But such capabilities would require an understanding of physics far beyond current knowledge. It would require control over energies and materials that may not be attainable. The gap between theory and practice is vast. There is also the idea of gravitational sailing. A craft could ride the curvature of space-time shaped by massive objects. It could be flung outward by gravitational assists from stars and black holes. This method works well within galaxies, where gravitational sources are common. But between galaxies, the void is too empty. There are no large objects to provide the necessary boosts. If travel across the void seems impossible, communication might still be achievable. Light travels freely. A message encoded in a narrow beam could cross the gulf in a little over 2 million years. Such messages could be sent regularly. A distant civilization in Andromeda might broadcast a signal toward the Milky Way, hoping that in millions of years someone would receive it. The timing would not matter to them. They would broadcast into the future. But humans think in shorter spans. Waiting millions of years for a reply challenges every instinct. Communication across galaxies is communication with future species, not current ones. It becomes less about dialogue and more about legacy. Messages across intergalactic space are time capsules. They are attempts to speak with descendants who will not share the same cultures, languages, or perhaps even biology. Human scale helps clarify the situation. Imagine writing a letter and casting it into the ocean, knowing that it might reach a distant shore long after your civilization is gone. The act is not about hearing a reply. It is about sending a fragment of your story into a larger sea. Crossing the void is like that. Even if travel is impossible, communication is a gesture toward continuity. There is another angle. Perhaps the void is not crossed by individual journeys. Perhaps galaxies cross it for us. Andromeda is already drifting toward the Milky Way. In billions of years, the two galaxies will merge. Their stars will intermix. Their clusters will merge. Their worlds will drift into new orbits. Any civilizations that exist in that era will share the same galaxy. They will no longer be separated by a gulf. They will be neighbors within the merged system. This raises a deeper question. If intergalactic travel is impossible for civilizations at our level, what does that say about contact? Does contact depend on the natural motions of galaxies? Will communication become easier only after mergers bring systems together? Perhaps the cosmic web shapes not only the structure of galaxies, but the possibilities of connection. Where galaxies cluster, civilizations could encounter one another. Where galaxies drift apart, isolation grows. Speculation aside, some ideas hold firm. To cross the void with known physics requires time beyond human experience. To travel through speculative physics requires breakthroughs not yet imagined. To communicate requires patience measured in millions of years. And yet the question remains valuable. It reminds us that we inhabit one part of a much larger structure. It pushes the imagination outward. Think of the void as an ocean. Some boats never cross oceans. Some cast messages in bottles. And some wait for the tides to shift. The space between galaxies is not a barrier placed to limit us. It is simply one of the scales at which the universe operates. If we wish to understand our place in it, we must think beyond lifetimes. These impossible journeys set the stage for a stranger thought: the galaxies themselves are already on a collision course that will do the traveling for us. The future of the night sky does not unfold quickly. It happens in slow motion, across spans so long that the human mind must stretch to imagine them. Yet the motions themselves are already underway. Andromeda approaches the Milky Way with a steady pull. The distance shrinks by hundreds of kilometers each second. Nothing dramatic changes from year to year, but the path is fixed. The two great spirals are drifting together across the dark, drawn by a mutual gravity that outweighs the expansion of space at their scale. From a quiet world inside the Milky Way, the first sign of the merger would be subtle. Andromeda would appear slightly brighter over millions of years. Its blurred form would sharpen. The spiral arms would become more distinct. Over an even longer span, the galaxy would grow in apparent size. The faint smudge that once hid in the night would become a visible giant rising above the horizon. Its stars, still distant, would reveal structure never seen before by human eyes. As the galaxies draw nearer, their halos collide. These halos, composed mostly of dark matter, interpenetrate long before the visible disks touch. Their masses begin to mix. The gravitational fields distort. The stars within each galaxy respond to this distant pull. Their orbits stretch and twist. Some stars are flung outward into wide arcs. Others begin drifting into new paths that lead them from their native spiral arms. Long before the first visible collision, the invisible architecture has begun the transformation. Then comes the first passage. The disks sweep past each other, not as colliding solids, but as interwoven clouds. The distances between stars are vast. Collisions between stars are extremely rare, but gas clouds feel the encounter. They compress. They ignite bursts of star formation. Entire regions flare with new light. Blue clusters appear, dense with young stars. Shock waves ripple through the gas. Tidal tails extend outward like luminous bridges. The galaxies distort each other, each drawing long streams of stars from the other's disk. If you could stand on a world during this stage, the sky would be unlike anything seen today. One horizon might show the shredded remains of the Milky Way's own arms, stretched into faint arcs. The opposite horizon might show Andromeda's bulge rising in distorted form. The night would contain knots of new star birth brighter than any nebula visible now. Patterns of familiar constellations would vanish. A new sky would emerge, one with no stable map. After the first passage, the galaxies swing apart briefly, but their mutual gravity is too strong to let them escape. They spiral inward. Each passage draws them closer. Their shapes become more chaotic. Tails fold back. Streams intermingle. Clusters that once belonged to isolated dwarf galaxies now move through the combined gravitational field of both spirals. The process takes billions of years, but time does not diminish the inevitability. Eventually, the cores approach. When the central regions merge, the history of both galaxies is rewritten. Gas clouds sink toward the new common center. Star formation may surge again. The two supermassive black holes spiral inward, losing energy through gravitational interactions with surrounding stars. They circle each other until they finally coalesce into a single, larger black hole. A burst of gravitational waves travels outward, carrying the final signature of the two cores' union. The center of the new galaxy brightens as it adjusts to its new shape. The merged system eventually settles into a new form. Simulations suggest it may resemble a large elliptical galaxy. The familiar spiral patterns will be gone. The new galaxy, often called Milky in models, will contain stars from both parents. Its halo will be the combined mass of two ancient structures. Its streams will be tangled, its clusters will mix. The Milky Way and Andromeda will no longer exist as separate identities. Their names will become historical artifacts. This is the moment of the chapter's central reveal. In the far future, after the merger has settled and cosmic expansion continues, the new galaxy may become isolated. As the universe accelerates, distant galaxies will fade beyond the horizon. Their light will never reach the merged system. Astronomers living in Milky may see no evidence that the wider universe was once filled with galaxies. Their observable cosmos will shrink to the stars of the merged galaxy alone. The grand history of the universe will no longer be visible from where they stand. For future sky insights ahead, hit like and subscribe to the Quiet Universe channel. The implications are profound. The next great civilization, born long after the merger, might believe the universe contains only one giant galaxy. They might never discover that their home was formed from two spirals. They might never know that billions of galaxies once filled the sky. Their instruments would detect a universe composed of a single island of stars, adrift in darkness. Human scale brings this to life. Imagine a world orbiting a stable star deep within the merged galaxy. Its night sky shows no trace of the Milky Way's band, no trace of Andromeda's bright core. Instead, it shows a smooth distribution of stars, with no defining structure. If its inhabitants looked outward with curiosity, they would find only darkness. They would not know that the darkness once held the lights of countless galaxies, receding beyond sight as the universe expanded. Yet some traces will remain. Long streams of stars from both galaxies will wrap around the merged core. A few compact remnants of dwarf galaxies will orbit like ancient relics. The central black hole will be more massive than either of its predecessors. These clues, if read carefully, could hint that the galaxy was not born whole. A patient and skilled civilization might deduce its dual origin, but they will not see the Milky Way or Andromeda as separate forms. Those shapes will be myths reconstructed from scattered evidence. The merger itself may create new chances for life. Gas compressed by tidal forces may ignite waves of star formation, producing new clusters where planets could form. Some stars may be flung into the halo, giving rise to worlds with quiet skies and little interference. Others may fall into denser regions, facing harsher environments. The merger will not eliminate habitability. It will redistribute it. Eventually, the new galaxy stabilizes. Its stars circulate within a redefined gravitational field. The merged halo extends outward, smoother, but still filled with remnants. Over long ages, the shape of the new galaxy becomes familiar. If anyone lives to witness it, they will know their home not as the afterimage of a collision, but as the only cosmic continent they have ever seen. Once the merger is complete, the next question is not what happened to the spirals, but what it means to live in a universe where the evidence of a grander past has slipped beyond reach. A quiet world orbits a steady star somewhere in the deep future. Night has fallen there, but the sky looks nothing like the sky we know. No river of the Milky Way cuts across it. No smudge of Andromeda rises gently above the mountains. Instead, the heavens glow with a smooth scattering of stars. Bright, but unpatterned, neither spiral nor banded. The people of that distant epoch might lift their eyes and believe their galaxy has always been one thing, one shape, one history. They would not know that two great spirals once rushed together through the dark. They would not know that the universe once shimmered with billions of galaxies beyond sight. This imagined sky is not fantasy. It is a projection of modern cosmology. The merger of the Milky Way and Andromeda will unfold slowly, reshaping both galaxies into a single new system. After that merger settles, the accelerated expansion of the universe will pull distant galaxies over the horizon. Their light will never reach the merged system. The inhabitants of that age will see only the stars of their own galaxy. They will live in a cosmos that appears smaller than ours, hollowed by distance, quiet in a way we can scarcely imagine. So the act of looking ahead becomes a kind of reflection. What does it mean to live inside a galaxy at all? What does it mean to build meaning in a universe that rearranges itself over billions of years? Humans think in generations. Stars think in millions of years. Galaxies think in billions. And yet the effort to understand any of them is a human act, shaped by curiosity and guided by the fragile span of a single lifetime. A galaxy is not a permanent shape, it is a momentary pattern in a long, evolving field of gravity. Everything solid inside it is temporary. Spiral arms wind and dissolve. Clusters move outward. Disks warp. Streams unravel. Even the stars, blazing and steady to our eyes, change over time. If a species builds its identity on permanence, a galaxy will eventually contradict it. But if a species builds its identity on curiosity, a galaxy becomes a teacher. Look again at the path that brought us here. A faint blur in the sky revealed that the Milky Way was not alone. The discovery that Andromeda was another galaxy expanded the human understanding of space. The realization that Andromeda approaches the Milky Way expanded the human understanding of time. The study of its halo revealed the long memory of stars. The analysis of its chemistry revealed a lineage of collisions. The mapping across wavelengths revealed that every portion of the galaxy carries a different truth. And the questions of habitability reminded us that life, if it arises anywhere, arises in pockets of stability carved out of chaos. These insights were gained not through conquest or reach, but through careful attention. A telescope on a mountain, a spectrum on a glass plate, a faint line that shifts by a fraction, a longer exposure that shows a hidden ring. Each discovery unfolded slowly, layer by layer, building a story larger than the instruments used to reveal it. If future observers in the merged galaxy know their true history, it will be because a species in the ancient past learned how to read faint light with care. Imagine the scientists of that far age. They live inside a galaxy that remembers too much and reveals too little. They look outward and see no spirals beyond their own. They see no distant clusters, no cosmic web, no lattice of galaxies threading through space. They see only the stars of the merged system, arranged without the familiar order of spirals. Yet if they examine their own halo, they will find streams. If they measure those streams, they will find chemical patterns. If they map those patterns, they will notice inconsistencies. They will find clusters that orbit strangely. They will find stars enriched by processes that suggest two parent galaxies, not one. Their own sky will become a puzzle, and their work will echo ours. A quiet question grows from that thought. What would they conclude about themselves? Would they guess that their galaxy had a dual origin? Would they piece together the story of two ancient spirals drawn together by gravity? Would they find traces of the Milky Way in the metallicity of one region and traces of Andromeda in the chemistry of another? Or would they accept the sky as they see it, unaware that the silence outside their galaxy hides a richer past? The question turns inward as well. What do we conclude about ourselves? We live in a moment where the sky is open. We can see beyond our galaxy. We can map the motions of others. We can observe clusters at the edge of the observable universe, but our window is temporary. The sky of the far future will be narrower. Our era is one in which the universe appears full. Our descendants may see a cosmos that appears empty. This suggests a responsibility, not a duty to travel or to conquer, but a duty to understand. The information we gather now may one day be the only record of a universe far larger than the one future observers will perceive. In this sense, every measurement, every spectrum, every map becomes an act of preservation. To study the cosmos is to safeguard its memories. At its core, the story of the Milky Way and Andromeda is not a story of collision, but of continuity. It is the story of two galaxies whose histories stretch back to the early universe. It is the story of countless stars living and dying. It is the story of clusters that survived mergers and streams that trace ancient paths. It is the story of gas that cooled and condensed into new beginnings. It is the story of dark matter shaping everything from the first flickers of light to the present day. It is also the story of meaning. A galaxy has no intention. It does not know its own path. It does not remember its own mergers. But those who observe it do. Thought is the fragile element that attaches meaning to motion. Consciousness gives shape to the vast. A star burns whether or not someone watches. But a star becomes part of a story only when someone sees it. In this way, the universe does not ask us to endure. It teaches us how. It shows that even the largest structures are temporary. It shows that change does not erase beauty. It shows that endings can be woven into beginnings. A galaxy that meets another galaxy does not vanish. It becomes something new, and in that transformation lies a quiet mirror for every conscious being that lives within it. Near the end of this reflection, consider a thought shaped by countless measurements and quiet hours at the edge of darkness. We do not escape the universe by understanding it, but we refuse to be only scenery. To measure the cosmos is to become part of the conversation that unfolds between matter and meaning. So imagine the last image of this act. A distant world in the merged galaxy. Its night sky smooth and deep. A thinker stands beneath that sky, gazing upward. They see only one galaxy, but in the faint currents of its stars, they sense that it was shaped by events older than any memory. They feel the pull of something vast. And they wonder, perhaps for the first time, whether their night once held more than they can see. When the last island of light floats in an almost empty universe, will someone there still look up and ask not what is out there, but what kind of story they are inside?